In 1968, 1 year before Apollo 11's landing struts settled into the lunar soil, Dr. Peter Glaser proposed a method for collecting energy in space and delivering it to Earth. Space-based solar power is not a new concept, yet to many it seems to be a foreign and insurmountable task. And for good reason. Creating and launching a sunsat that will rotate in sync with the Earth, beaming continuous green power, is no small challenge. Geosynchronous orbit, located 36,000 kilometers above Earth, is simply too far away. It would require an immense array, coupled with ungainly transmission technology, to beam energy to Earth from this orbit. Even if the transmitter satellites and their solar panels were to be launched in pieces, they could not begin to provide a return on their substantial cost until they were fully assembled. So are we to abandon space-based solar power, relying on fossil fuels until we inevitably choke on our stubborn reliance on unclean power sources? Will terrestrial solar power and other current energy alternatives, so dependent on an abundance of open land, be sufficient to sustain our ravenous appetite for energy? This challenge requires a deviation from the present course of thought. And sun-synchronous orbit is the answer. It is a proven orbit, as Canada's RadarSat-1 has demonstrated every 100.7 minutes since 1995. Placing a solar power transmitter in sun-synchronous orbit will not have the graceful simplicity of one satellite providing constant power to one location. Instead, it will require a constellation of interconnected satellites. Some satellites in the constellation will collect and transmit energy, while others, known as reflectors, will bounce the energy to pinpoint locations on Earth. It is a realistic objective, one that can be completed with current launch systems and technology. The Falcon Heavy, whose maiden launch is set for 2013, could lift an entire constellation of 10 reflectors into 4,000-kilometer equatorial orbit. That same launch efficiency will carry the transmitter satellites into sun-synchronous orbit, and those transmitters could start providing a return on investment days after launch and placement. In this innovative design, each reflector, traveling on an equatorial orbit, will have a 9-minute window during which power can be sent anywhere on the globe. And when one reflector leaves the range of a north-south traveling transmitter satellite, another enters the power sat's range and takes its place, providing continuous power. The key advantage of a sun-synchronous orbit, as compared to geosynchronous, is the incredible reduction in size the closer orbit enables. SSO reduces the energy delivery distance from 36,000 kilometers to a mere 8,000 at maximum. Satellites can be smaller, much smaller, and with an average launch cost of $10,000 to $25,000 per kilogram, a 90% reduction in weight is the difference between dream and reality. Utilizing sun-synchronous orbit will put space-based solar power on a plausible timeline for implementation, with technology that exists now. It is the next generation that will suffer if we continue on our current path, and to spare our children the consequences, a realistic solution is exactly what is needed.